So welcome to this first colloquium of the academic year. The colloquium is devoted to cosmology, and my colleague Andrea Ferrara will introduce the speaker shortly. As of today, the next colloquium should be held on November 20 and should be devoted to biology. Thank you.
So good afternoon, everyone, and it's a pleasure and an honor for me to introduce today's speaker for the Colloquio della Classe, and it's Professor Massimo Stiavelli. Massimo is actually at the Space Telescope Science Institute in Baltimore, US. So Massimo has been a former student or alumnus of the Scuola Normale, and he also got the PhD from here, and then he decided that he wanted to go to the US, and he moved to the Rutgers University, where he spent some time before coming back to Europe as a ESO fellow, and then he decided that he wanted to go back to Pisa, so he got a position here as a tenure-track researcher at that time, but then he decided that he wanted to go away from Pisa again, and so he went back to the States, and he started to work at the Space Telescope in Baltimore, and immediately got involved in the missions that the Institute was operating at that time, and in particular the Hubble Space Telescope, which is the precursor to the James Webb Telescope that he will describe us today. So he developed several instruments for the Hubble Space Telescope, in particular 3 different cameras that have been very successful and very useful for all of us. And then he started to work on JWST, and he became the mission head, so a very important role. And so he governed the deployment and the design and the deployment of the telescope from 2008 to last year, essentially. Now he's in sabbatical, so having some rest over all that hard work, and he's an expert on early galaxies, first stars, and in general he has worked on a number of different topics, mostly related to the distant universe. So today he will tell us about studying distant galaxies with the James Webb Space Telescope. Thank you, Massimo.
Thank you for inviting me, and thanks for the very nice introduction. I was hoping that the colloquium would be held upstairs in the Sala degli Stemmi, because they would have allowed me to point out that my last talk in that room had been in November '86 when I defended my thesis, but I'm still get to make the point, even one floor down. So. Again, it's great to be here, and this is, I won't spend much time on this, but this is almost an arc of going from being a theorist to being an experimentalist, to building things, and then going back to using those things to take data, and maybe someday I can become a theorist again, violating the Shama principle, perhaps. So. I'll talk about the precursors to the James Webb Space Telescope, which is the next generation space telescope, and how that concept came about. Then I'll say a few words about building the James Webb Space Telescope, and then I'll describe some science results, focusing mostly on my data, rather than giving an overview of everything that James Webb has done. First of all, that would be a talk on its own. There is a lot of work that has happened. And the second is that I applied for a position in the Science Working Group about 20 years ago, and I waited 20 years to get my data, so I kind of feel attached to them. The work on the Next Generation Space Telescope was kick-started by the Hubble Servicing Mission in '94. This is the mission that removed spherical aberration from the Hubble Space Telescope, adjusted the optics, restoring the optical quality that was supposed to be there. And in '95, we did the Hubble Deep Field, And that revealed, that's the image on the left, which now by present standard is awful, but it was great when it was done, revealed that there are a lot of galaxies that are small and exist at high redshift. A redshift is a way that astronomers measure distance. It's actually a measure of two things. The ratio of the scale size of the universe now and at some time in the past is given by 1 plus z. So if you go to a redshift of 9, it means that the scale length of the universe was 10 times smaller than. And it also happens to be what happens to the wavelength of light. Light emitted at redshift 9 arrives here redshifted by a factor of 10, 1 plus z. So we use it to indicate, distance, and it gives us immediately information about the change in wavelength of light. Those observations told us that we're more likely a lot of higher redshift galaxies that we didn't see with Hubble, and that it would be nice to obtain spectra to measure their properties. People got to work and produced a document that was fed into the National Academy of Sciences Decadal Survey. This is the American process to decide the priorities for the next decade. So this is like a little summary of what this particular NASA flagship went through. The first ideas actually were proposed in 1989. This is Riccardo Giacconi was director of the institute. He knew that it takes forever to build the NASA flagship. And so he worried that, with Hubble, there wasn't launched yet, was expected to be launched in 1990. And with a lifetime of maybe 15 years, he worried that by the time Hubble reached the end of life, we wouldn't have a successor. So he wanted to pose the problem, what do we do after Hubble? Then, of course, Hubble lived a lot longer than that. However, when spherical aberration was discovered upon launch, that, of course, put a freeze on everything. And nothing happened until it was repaired successfully. And so in 1996, NGST restarted. We came out with a yardstick design. This is a kind of notional proof of concept that you can have a design that presumably works, credibly works, and it would fulfill the requirements. Then an ad hoc science working group was created to kind of broaden the science theme. The initial idea of NGST was that it was the first light machine. But of course, if you want support from the whole community to build something that is so expensive, and so it needed to be broader than just first light. It was descoped from an 8 meter to a 6.5 meter diameter telescope. Then an interim science working group was created to still nurse the science case. And one of the things that this group did was to add moving targets. We were supposed to be very simple and not to be able to track, say, comets. When we talk about moving targets, of course, we mean things that move fast because, since everything rotates, we need to be able to follow things that move slowly. But, a comet is very fast and it's a whole different story, or a planet. And so we needed to add moving targets to broaden the science case. And then the Flight Science Working Group was created and the prime contractor was selected, which was Northrop Grumman. And I had the fortune to be part of all of these groups. So I was really there sometime. For Calvino, for Italo Calvino fans, I feel a little bit like the old QFW FQ. I was there at all the stages. So anyway, took about 20 years of actual development, cutting metal, as they say, about 10,000 people. And this is actually funny because one of the things, when I was here as a student in the Corso Ordinario, I wasn't really sure at the beginning whether to go into astronomy or still theory-oriented, but maybe particle physics. And there were two deciding factors. One was a course on finite representations of finite groups, for which I had no intuition whatsoever. And the second one was that I thought in astronomy, a small group of people can do research, while in particle physics, I was seeing my colleagues that were working in these huge groups. And I thought, I don't want to be part of a huge group. I want to be in a small research group. So anyway, 10,000 people. And then one thing that we did, I think right, was that all these science working groups that I told you about held the high-level science requirements. We did not compromise. These, of course, doesn't help reducing the cost, but it helps in keeping the mission meaningful. Because throughout the years, and whenever we had a cost increase, the National Academy, other bodies would be asked, is it still worth doing? And because of the way we had designed it, it was. Nothing else could do that science except that telescope. And there are other missions that instead descoped their requirements, and they ultimately were canceled because they were no longer unique. So this is probably one of the reasons why we survived. The picture there is an example of the people at Goddard, NASA Goddard, which is a NASA center close to Baltimore. And it's only some of the people working there. Of course, the group is much larger. The Space Telescope Science Institute ended up being the Flight and Operation Center, the Flight and Science Operation Center for JWST. For Hubble, we only do science operations. We prepare the schedule, select the proposals, process the data, archive the data, distribute the data. For JWST, we even do flight operations, so actually maintaining the hardware, making sure the batteries are charged and we are not looking where we should and the health of the spacecraft is okay. So it's a step up. And I was first project scientist, then in 2012, I became mission head, which means essentially managing about $100 million of funding and prioritizing the work for 300 people. So that's pretty far off from doing dynamics of galaxies. Here is a sketch. Spitzer Space Telescope, very small. Was the previous infrared telescope that NASA developed. Hubble in the middle, and James Webb shown there, a single segment. The aperture has 18 individual segments. A single segment is larger than Spitzer. The reason of the diameter is twofold. We wanted to have the angular resolution in the infrared that Hubble has in the visible. So if you want to have the same angular resolution and you have a diffraction limited telescope where essentially lambda over d determines your angular resolution, wavelength divided by diameter, you want the same angular resolution as Hubble at 3 times the wavelength, you need 3 times the diameter. So that's one of the drivers. The other one is that we wanted an infrared telescope for essentially 3 reasons. The first historical reason was to look at these very distant galaxies. As I said before, very distant means very redshifted. The light that these galaxies emit in the ultraviolet or visible ends up in the infrared. So you need to look for it where it lands, in the infrared. And the second two was that as we were broadening the science, we wanted to see dust-enshrouded systems in the Milky Way, for instance, star-forming regions in the Milky Way. So you need, again, the infrared to penetrate the dust and see these objects. And also we were interested in molecules that are recognizable in the infrared. And the telescope is at the Lagrangian point L2 of the Earth-Sun system. For those who remember the Lagrangian points, L4 and L5 are the stable ones if the mass ratio is right, and the other ones are non-stable. They are settled points in the potential. So if you are in L2, you need fuel. Otherwise, on a folding time of the order of a month, you start drifting away. So you need to use your rocket engine to stay near the equilibrium point. So here are a few things. While building this thing, we had to essentially develop 10 new technologies. I won't mention them all. One was the technologies for the mirrors, because nobody knows how to polish a mirror at an ambient, at the temperature of this room. Sorry, everybody knows how to do it at this room. Nobody knows how to do it at 40 Kelvin. We were building a telescope that was supposed to operate at 40 Kelvin. And every material deforms significantly, and we wanted mirrors that had a surface accuracy of 14 nanometers RMS. So you want something that has this accurate surface to 14 nanometers RMS at 40 Kelvin, but you polished it at ambient. So it needs to have a very highly reproducible deformation so that you shape it in the wrong way, so to speak, in ambient, that it will deform into the right shape at 40 Kelvin. And that is what led us to choose beryllium for this, because no glass at the level of reproducibility. And so it's gold-coated beryllium, 18 segments plus the secondary. And it worked. On the lower, maybe I can use the pointer. This is the mirrors. Here, you have the instrument module. These are the 4 instruments all packaged up. They were put together into this thing that is called OTIS, Optical Telescope and Instrument Assembly. And the telescope is looking toward the wall here. And this thing had to be tested at Johnson in Houston, and in Chamber A, which is this thing here. This is where the Apollo command module was tested. So after the Apollo program, this became a national monument. So we had to obtain a waiver from the National Park Service to have permission to modify it. And the reason we needed to modify it is that we wanted to push the temperature down to 40 Kelvin. And so we needed an helium shroud inside to push the temperature lower. And the thing that had to be at 40 Kelvin was about 3 tons of OTIS plus the support structures. So you're talking about multiple tons that had to be kept at 40 Kelvin for the durations of many weeks, which means essentially several trucks of liquid helium per day. And to move it from Goddard to Johnson, we used that transport container you see in the center of the picture that barely fits into a C5b galaxy. Then in Northrop, they were developing the sun shield that you see on the lower right, the 5 layers with a guy in the middle for size. And then all the pieces went together in Northrop. And that's the last picture there when everything gets put together. So it's an infrared telescope, the largest put in space, 6.5 meter, 4 capable instruments. 2 things having to do with the instruments are also new technologies, or relatively new technology. One is that, even though I've been talking about 40 Kelvin, the mid-infrared instrument that goes to 28 microns in wavelength uses a detector that needs to be cooled to 6 Kelvin. And so we use a closed cycle cryocooler. And with the requirement of launch and so on, these had to be a new technology development. And the other one is the MEMS slit selection. We have this MEMS system, microelectromechanical system, that's an electron microscope picture. It's 248,000 microshutters. Each can be commanded individually to be open or closed. And that allows you to open slits where you need them. So to select certain objects instead of other objects. And that's part of the near-spec spectrograph, which is built by the European Space Agency, but that's a US contribution. The whole telescope is an international collaboration, of course, between NASA, the European Space Agency, and the Canadian Space Agency. The primary mission was supposed to be 5 years, with a goal of 10 years. And we were, as I mentioned, the Flight Operations Center. You see here the flight control room, a picture of the flight control room during commissioning. the deployment of the telescope involved 178 release mechanisms and 132 actuators. They were all single point failures. So when you have 178 single point failures, the reliability of each component better be 0.9 with enough number of nines that to the power 178 is still close to 1. And it turns out that that number of nines is between 5 and 6. So, that's how challenging it was. This is the last time I saw it at Northrop. The sun shield is not fully deployed, the secondary is not deployed, and the wings on the side are retracted. But anyway, that's the telescope in all its beauty. The pictures had to be taken by a Northrop photographer because other photographers could accidentally take pictures of things that the world is not supposed to see. I haven't figured out what that was, but that's what they said. So here's the launch. Unfortunately, we can't hear the countdown in French. The telescope went by boat to French Guiana and was launched on an Ariane 5 ECA. We had to give a little, they were very collaborative. We had pressure requirements on the shroud that were tighter than anything that Ariane had launched before, so they had to redesign some vents and so on. And for the first time, they put a camera on the upper stage as a test. This is now standard on the Ariane 6, but it was the first Ariane 5 with a camera. And that camera, let's see if we see it. Showed us this. So this is the actual telescope separating from the upper stage. Those two things you see here are the main thrusters. And these things are the sun sensors that help us figure out where we are pointing. Occasionally you see a blue light. Those are the little rockets that we use for adjustment of the position, rotation, and so on. And occasionally you'll see them firing. The launch was so, right now, the launch was so perfect that the automatic software was that they would deploy the solar panel when the telescope was sufficiently stable with, not moving in any funny way. And we could, of course, command it from the ground. And that condition was met early, and so the telescope deployed its solar panel. And it's this point that I was pretty happy, and I ran from the room with a big screen to my office to follow the rest that was happening that day. I think, I don't know if we saw it earlier or we were over the Horn of Africa, Saudi Arabia, and so on at that point. So, what happens next? What happens next are all those deployments, and here's a video. Of course, I don't have a video for the deployments. This you already saw. From the minute 30 onwards, we were commanding the telescope from Baltimore, receiving the telemetry and giving the commands. This is the mid-course correction 1A, the big burn that puts us on the trajectory to, let me stop maybe, on the trajectory to L2. The launch date of Christmas, from the point of view of orbital dynamics, was very good. Ariane did a fantastic job, and so we were on track to have a lot of fuel left. The last thing was on us to do the mid-course correction 1A well. And the reason that's tricky is that in order to do exactly what you do, you need to know exactly where the telescope is. So you need to do the mid-course correction after enough hours that the telemetry from the ground has triangulated the position of the telescope accurately enough that you know exactly where you are. But if you wait, the more you wait, the more fuel you'll need to spend. So we did a lot of exercises for launch and so on, as you can imagine. In one of the exercises, we ended up doing it several hours after the nominal, and those several hours reduced the lifetime from 10 to 8 years because we used too much fuel. So that was a little bit of a tense moment, and we did it at 12.5 hours after launch, exactly when it was supposed to happen. And right then, I knew that we have fuel for more than 20 years. Of course, NASA, being conservative, didn't announce it until a month later. But we all were smiling and knew that it was good. And by the way, this shows where the telescope is. So when it was in this shape, it had already passed the moon. And you see the various components. This is the momentum trim flap to make sure that the pressure from radiation and solar wind is balanced. Here are the releases of the covers of the sun shield. The sun shield is deployed. This was, to me, the most anxiety-generating moment, because the sun shield was the most, I think, complex thing that we had on board. And then the secondary mirror, some radiators, the wings, and from then on, essentially two things had to happen. One was work on the optics, and the other one, it had to cool down. I don't want to show you that twice. The work on the optics for people here who do experimental work is interesting, because the segments, the mirror segments, were on launch supports. And so they had to deploy away from the launch support in order to be adjusted. The adjustments had to be done with an accuracy of 1 nanometer. But the disengage from the launch support involves a movement by almost 1.5 centimeter. So you have to have something that has a 1 nanometer accuracy, but a range of 2.5 centimeters, as it turns out. So this is not totally trivial, apparently, but it worked. So this is the commissioning. The first month is the deployment, as you saw in the video, plus cooling, just radiatively cooling away. That wasn't exactly, watching TV, because when you have something like this, you are afraid that some parts, despite all of your care, are carrying water. And water has the bad habit that in space, it will move to the coldest surface and form ice. And we have seen many missions that occasionally say, oops, we had some ice where we didn't expect it. Well, the problem is they should have expected it. And so you need a plan that the coldest surface at any time is one that you wouldn't mind it got water on. So the most critical ones have to be the ones that are cooled last. And so that was part of the problem. Then for about 2 months, we had to align the telescope, and to get, took about half that time to get the first sharp image. And then the remaining 3 months, the remaining 2 months are the commissioning of the instruments, making sure that all the modes work and everything is okay. So one thing that I'm pretty proud of is that based on our pre-launch plans, we were supposed to get to the fully, not cooled down, but the fully deployed configuration after 4 days, 2 hours, 40 minutes. In real life, we got there after 14 days, 3 hours, 8 minutes, 28 minutes late. So I think this is pretty good considering the complexity of what was being attempted. Oh, and by the way, since it was too easy otherwise, of course, nature threw us a few, extra challenges. For instance, while we were testing the optic at Goddard, we had what was nicknamed Snowzilla. a huge snowstorm that blocked everything. So people were sleeping in the at Goddard because it was unsafe to travel home and back and so on. So that was one. When we went to Johnson testing, we had a hurricane hit Houston. Again, people sleeping in the center. People had to put out tents because it was raining into some of their offices because they were not used to that much rain. And when we were in California, we had a small earthquake, but nothing to, it had been designed to resist much bigger earthquakes, so that wasn't a problem. So, and of course we had COVID throughout commissioning. In particular, the critical phase, we were in what in the US was the Omicron peak. And so we had particular strategies to deal with that, and it worked. So the summary is the WST beats requirement in every area, which is kind of unavoidable. If you have requirements with margin, there is a chance, if everything works, that that margin transforms into extra ability. So the optical quality, we were supposed to be diffraction limited at 2 microns. We are diffraction limited at 1 micron. We were, in fact, a little less than 1 micron, but then we had the bigger than expected micrometeorite hit that puts us at 1 micron. The telescope is very stable. We need to correct the optics less frequently. The observatory itself is very stable. For something this floppy, it's amazing that we can hold the point into 1 milliarc second for over an extended period of time. The sensitivity is better than expected in most modes. We can track moving targets faster by a factor exceeding 3 than the requirements. When there was the mission to hit the double asteroid Didymos, we were asked to look at it. And our requirement was 30 milliarc seconds per second moving target. And this thing was moving at 105 milliarc seconds per second, and we were able to take the picture. And the lifetime is, at least the fuel, of course things could break, but the fuel is more than 20 years. So in principle, we can do better science for longer time. This is a picture that normally is not representative of how the telescope is used. The instruments are all on, but because of data volumes and other characteristics, we typically don't take data with all instruments in parallel. So we take data with 2, occasionally with 3 instruments in parallel, but this is kind of an illustration of what you would see if you took instruments. So NIRCam is the camera, the near-infrared camera, going from 0.7 to 5 microns. NIRSpec is the spectrograph, multi-object spectrograph with those microshutters. MIR is the mid-infrared imager and spectrograph. NIRIS is a Canadian contribution. It's a slitless spectrograph and backup imager. And the fine guidance sensors are the ones that keep us pointed with accuracy, but they can also, on a pinch, take images. So the science goals were 4. Looking at the first galaxies, study how galaxies evolve, discover how stars and planets are born, and the origins of life. As we were designing the telescope, a lot of exoplanets were discovered, and we found that we could do good exoplanet science. So in the rest of the talk, I will talk mostly about distant galaxies, but I want to say one thing about exoplanets. So this is, for the cycle 1, the exoplanets that JWST was planning to observe. The squares and red dots. For reference, the Earth and Jupiter are shown. This is the temperature of the planet and its radius. So a range of planets going from as small as the Earth to much bigger ones and much warmer. What we want to do, I don't like that. So we use mostly the transit technique. This is when the planet passes in front of its star, When the planet, good point, Andrea. When the planet passes now in front of its stars, it creates a microeclipse, which of course is very small because the planet is much smaller than the star. Some of the starlight goes through the atmosphere of the planet. So molecules in the atmosphere of the planet, if the planet has an atmosphere, will leave an imprint on the signal. So if you take data during the transit and before and after, and your spectrophotometry is, say, 100 parts per million or better, you can actually measure the composition of the atmosphere of that planet. And that's, that's the dream would be, this is for the solar system, Venus, the Earth, and Mars, would be to find something that is not just like Venus or Mars, but has ozone, water, and so on. And for terrestrial planets, we're still working on it. For gas giants like Uranus, Neptune, Saturn, Jupiter, it's done regularly because they are much bigger and it's easier to do. So this is an interesting field of research that was unexpected at the beginning. So going back to my field. So here's a sketch of the Big Bang. The cosmological nucleosynthesis produces essentially hydrogen and helium and very little else. So most of the chemical elements we have around us are made in stars. Of course, the first generation of stars was created from mostly hydrogen and helium. So that first generation is different from all the other following stars. And since astronomers like to be simple in their names, we call this first generation of stars population 3 for simplicity. Anyway, these first stars have primordial composition and have very different properties from the stars we see around us today. And not one of them has ever been seen, but they must exist because we are pretty confident that about the cosmological nucleosynthesis. So these stars produce heavier elements, and then all the other generation of stars produce other elements. And I already told you about the redshift. The one thing I didn't tell you yet is that astronomers call metals everything that is heavier than helium. So lithium, oxygen, neon are well-known metals. So why do we care about metals? This is a simple sketch, but I think it carries the message. The same mechanism, stars produce energy by nuclear fusion. The same mechanism produces heavier elements and energy. So the metals and the energy. However, metals have more energy levels than hydrogen and helium, and with smaller spacing. And so these energy levels can be excited by collisions. And so when you excite in a gas collisions, levels by collisions, you are actually enabling radiative cooling because you transfer kinetic energy into levels that can be radiated, energy can be radiated away by photons. So the metal content in stars determines their effective temperature. Metal poor stars tend to be hotter, and determines also which stars you form, because the gas cooling that you need to form a star, it's easier if you have metals than if you don't. So we think that at low metallicity stars will be more massive. So we think that these POP3 stars will be not only hotter, but also more massive. How am I doing, Andrea? Okay, so a lot of us that were involved with the project wanted to use this telescope to understand the internal properties of galaxies. And one of the internal properties is the chemical composition, which ended up being easier to do than some thought. And this is from proceedings of a conference in Liège in 1998 that, in fact, Andrea attended as well. We were staying in the same hotel with Martin Rees. And this is an interesting plot because using strong lines of oxygen This is, I know. Strong line of oxygen and helium, or oxygen and nitrogen. You have a calibration into, this is a metallicity measurements. Abundance of oxygen, we add 12 because we like it. But anyway, think of it as log metallicity, log heavier elements. And you see it's a scatter plot. These strong lines don't yield a very good calibration. But if you have access to this little line here, then it's much more accurate as an estimator of metallicity. And so in this paper in '98, I argued, we should be able to use this thing with JWST. So, already told you about the metallicity. The strong lines are easy to measure, but give a crappy indication of metallicity. However, you can, in principle, obtain good measurements if you notice that, first of all, if you have two lines from the same ion that have different energies, that can act as a good temperature indicator. And if you have two ions that are roughly the same, two lines that are roughly the same energies, but have associated to different radiative transition probabilities, that becomes a good density indicator, because of course both states will be affected similarly by collisions, but one of them has a different radiative transition probability than the other. So what you see in the ratio of the two lines gives you an idea of the density. So when you have density and temperature, you can create a nice little model that gives you the abundance of that ion with high accuracy. And so this is essentially the basis of what we are doing. And so we can measure abundance ratios. And the other point that is worth making is that if you see the abundances in the sun, they are the result of countless generations of stars and contributions of stars with a range of masses. But once you go to high redshift, you tend to have fewer potential contributors. And I'll show this here. Traditionally in astronomy, people think of the alpha over iron as a clock. This is because alpha elements, which are essentially produced in type 2 supernovae massive stars through alpha capture, are formed immediately. These massive stars live few million years, explode, and pollute with elements like oxygen, the gas. Iron is instead produced by type 1a supernovae. These are supernovae that take a lot longer to form because they are based on the evolution of maybe binary stars and so on. So they take hundreds or even maybe a billion years. So often people in traditional astronomy think of the alpha over iron ratio as something that is high in the early times at low metallicities. And then as the type 1a supernovae explode, they produce iron but not oxygen. And so the ratio alpha over iron decreases, and we see this type of trend. However, at redshift 6 or greater, the age of the universe is less than 1 billion years. So you don't have time for type 1a supernovae. So this clock is useless for the high redshift. Almost useless, that we could have a discussion, but to first order is useless. However, we can have other abundances like carbon and nitrogen that can provide us with different clocks, and I'll show you a proposed example of that. Final thing, I don't know if I have time to go through this, but using photometry, so broadband colors, we can compute, estimate an approximate redshift. And then with spectroscopy, of course, we can refine it. But maybe if there are questions. So the first object I focused on is this guy. This was one of a handful of galaxies at very high redshift known before JWST. The reason I went to this one is that the redshift was higher than 9. And 9 is the highest redshift where I could measure the emission lines that I was interested in. And so as you can see, this is a Hubble picture. And this is the JWST picture at roughly the same wavelength, so you can see the improvement in angular resolution. The object is essentially invisible here because it's at higher redshift, and then it's visible in the other images. So these are spectra from that object. This is an interloper we don't care about. The object is this thing here. What you see, the line is essentially the continuum, and these little things you see here are the emission lines. And there are two things that I like about this. The first is that this is 1 to 3.5 microns, so near infrared. But in the res frame of the object, this is the ultraviolet. This is a carbon line at 1900 angstroms. So this object is at a redshift high enough that its res frame ultraviolet is detected by us in the infrared. So essentially the type of objects why we built JWST. Oh. And the other thing that I wanted to show is that, we see a lot of emission lines. This is H beta, for the Balmer lines, H gamma, H delta. There is an H epsilon here and some higher order ones, plus other elements. So you can do a detailed study of the composition. By the way, I would have, if you had asked me 20 years ago, I would have never guessed that I would be talking about chemical abundances, to be honest. With all respect for chemistry aficionados in the room, I would have been the last thing I would have thought. But this is what the telescope can do very well. So, and it tells us information. So it's a redshift 9.11. Looking at the Balmer line ratios that are to first order an indication of the presence of dust. Dust is the bane of astronomy because it can confuse the observations. We see that this object has essentially no dust. The 1 sigma error is compatible with no dust in the H gamma over H beta ratio. And using a line measure from the ground with ALMA, we can find that the electron density was 400 electrons per cubic centimeter. As I said, and so the density was one of the ingredients to do a detailed analysis. And we detect also that line, the 4363 oxygen line. And so with these two lines, we find the electron temperature to be 16,000 Kelvin in this equilibrium ionization region. And we can measure an oxygen abundance, which is roughly 1/6 of solar, and a carbon abundance, which is 1/6 of the solar ratio. But since oxygen is already 1/6 of carbon over oxygen means 3% of the carbon of the sun, 1/36 of the carbon of the sun. So this object is more metal poor than the sun and a lot carbon poor compared to the sun. So we think that this guy enriched in oxygen much faster than in carbon. And carbon is produced by intermediate mass stars that live longer than the ones that produce type 2 supernovae. So what I think happened in this object is that this is still in its first period of intense star formation. Some type 2s have exploded, have generated the oxygen. The intermediate mass stars haven't yet made the carbon. And this is verified by the fact that if I take the star formation rate that I measure and I look how much stellar mass there is, at the rate that I measure, it would make all the stars in 27 million years, which is small compared to the lifetime of the stars that make carbon. So it's a consistent picture. There is another aspect that I don't address in my paper, but Andrea and collaborators have addressed it. Where is the dust? Because we think that when you form stars, you need to form dust. And these objects appears to fit a model that has been built here in Pisa to describe the ejection of dust from a star-forming galaxy that is undergoing very intense star formation. And I believe this is right at the level that you need for that mechanism to work. So I think we have a consistent picture for this object. So we move to a larger sample. I'll say very quickly a few things. I believe that high redshift galaxies, the one we can detect, are bursty. They are not like local universe galaxies that have a little, star formation going on. And one of the reasons I think so is that this is a plot of the star formation rate versus stellar mass. This line, this red line, is an approximation of where the tau of star formation, so how long it would take to make the stars you see at the rate you see, is equal to the Hubble time, to the local age of the universe. So everything above this line is okay. They could have formed stars at that rate. Everything below this line, the universe is too young to have formed the stars that we see at the rate we see. So it means that these guys in the past had periods where they were forming stars more intensely than we see them now. Also, more than half the sample is above this line, and this is the line where the tau of star formation is 20% of the local Hubble time. So more than half the galaxies we see form their stars in less than 20% of the local age of the universe. So they took a much smaller time than they could have taken. So I think this is another ingredient to argue that star formation is bursty. Stars produce metals, and in the most simple-minded model that you could have, since if you make a kilo of stars, you make some fraction of a kilo of metals. Of course, the yield of metals depends on metallicity itself, some various factors, but to first order, this should be a tight relation. However, we miss a lot of metals. Some of the metals are recycled into other generations of stars, and they are not easy to measure. Some are ejected by winds. Some of the metallicity you measure is diluted by primordial gas that is falling into the galaxy. There are many things that complicate the picture. So it's hard to have a total metal budget. So the mass metallicity relation is observed, but is not as tight as one could in principle imagine. And this is the mass metallicity relation that we see using these precise metallicities based on these accurate measurements. And it has a pretty high dispersion. Different symbols are, these big ones are my sample. I added some from the literature. There are some lower limits. There are two things from this plot that I care about. One is this. We haven't seen a single object that has a metallicity which is less than 1/50th of solar. In order to have properties similar of these first generation of stars that I was talking about, you would need to go to 1,000th of solar. So we haven't seen anything that is even remotely approaching those first galaxies of first stars. And the second one, is the scatter. Is it okay? Is it not okay? Is it bigger than we expected? Maybe if it's bursty, that's what we should expect. But there is more work that needs to be done on that. Here I'm going into work that is unpublished, so, but it's fun. This is the nitrogen abundance. So nitrogen is made by different types of stars, and in the local universe, there is these little triangles and squares is the relation between the nitrogen over oxygen versus metallicity. Initially, it's sort of flat, and then it goes up. When we measure nitrogen over oxygen for our galaxies, and of course we have small number statistics here, which is one of the reasons why this is preliminary, we see some galaxies that are compatible with the local dwarfs, and some that are not compatible with the local dwarfs. And there are a number of explanations. Maybe there are a certain specific type of stars called Wolf-Rayet that produce extra nitrogen. Maybe there are more of them that have influenced this composition. Maybe there have been winds that have ejected oxygen. So when the intermediate mass stars produce nitrogen, we find an excess of nitrogen or oxygen, not because we have more nitrogen, but because we have less oxygen. Or maybe these galaxies actually were here, and because of dilution from infall of primordial gas, the metallicity has gone down, but of course the ratio between two species is unchanged because the material that falls in is primordial. Of this explanation, it's hard to pinpoint to one. My personal belief is that the last one, the dilution, is probably the leading explanation because galaxies are not isolated, particularly at this high redshift. They tend to have a lot of infall of primordial gas. Maybe I'll skip this. This is even smaller statistics. So essentially, I can measure the metallicity that the galaxy should have based on its mass. And so, does it have an excess or a deficit? Well, it turns out that the ones that have an excess in nitrogen have a defect in metallicity, which is compatible with their metallicity to be diluted by infalling material. And again, I don't want to take it too seriously at this stage. I won't say anything about that. So, near future, it would be nice to improve statistics, get also carbon, which is another clock that tells us different things, and explore fully the consequence of bursty star formation, both from a point of view of theory and getting additional data where we can look at galaxies with a spatially resolved spectroscopy where we see the individual clumps and we can do the analysis of each individual clumps. Some bigger question for the future is, at some point, we know that these primordial objects need to exist. We want to see them. And so, how do we find them? And there are essentially two ways that we could pursue. One is to go to higher redshift, because if there is this process of dilution, as you have primordial gas that falls in, it reduces the metallicity, and you have a chance to see pretty low metallicities even for galaxies that are not so small. The current record holder in redshift is a galaxy at 14.2 by Stefano Cardiani, who is here at the Scuola Normale. Measuring the abundances of that type of object is very, very hard. Another opportunity would be that maybe it's unavoidable since stars produce metals. If you really want to see low metallicity, you really need to go to very low mass galaxies, and that's also hard. And maybe we need to use a strong gravitational lensing to get an additional amplification, and people are of course trying all of these. And something else that I believe is also being tried, but requires extra luck, in my opinion, is to look for pristine cloud. If you have a pristine cloud of material that happens to be close to another galaxy, close enough to be ionized by that other galaxy, but distant enough that the chemical elements ejected, the winds from the other galaxy haven't polluted it, you could observe something primordial just because of that. And again, it requires a little bit of fine-tuning. So, summary, JWST is revolutionizing astronomy, including high redshift galaxies for which it was built. It's shocking maybe that we can measure precise chemical abundances in galaxies all the way to when the universe was 500 million years or old or younger. And these can, especially once you have a little bit better statistics, can help us understand the details of galaxy formation. In my opinion, the biggest JWST surprises are that we have not yet found an object in a robust way with a metallicity less than 1/100th of the sun. If you had asked me before launch, I would have said, oh yeah, I will find that quickly. No, we haven't yet. And so maybe we are not looking in the right spot. and I feel morally obliged to answer this question since we sold this telescope initially as the first light machine, and we haven't seen first light yet. Thank you.
Well, thank you very much, Massimo, for a fantastic presentation about JWST and the problems that you can hope to solve with it. Before I open the floor for questions, I recall that Massimo will be staying with us for 10 more days through the next week, and then he's sitting in an office at third floor in Palazzo d'Ancona. So if you're interested to talk to him, I'm sure he will be available. But also for students, if they want to have some past experience from an alumnus of the Scuola Normale. So questions? Yes.
So thank you very much for the talk. So I had a couple of curiosity. So just out of curiosity, is there a reason why the shape of the mirror is hexagonal? And then I wanted to understand how the shield, the sun shield, worked, and if you think that in our lifespan, then we'll be able to see this galaxy with this metallicity eventually.
So the hexagon is a convenient shape because it's easy to obtain from a circle, and hexagons tile the plane, so it's easy to build something with no big gaps by combining hexagons. And the reason I mentioned circles is that it's easy to clean, polish mirrors that are a circle, and then you cut the edges. This is not how we did it here, though. But you know, the tiling is a leading factor. The sun shield was, as I said, the most challenging thing because it's super complicated, and of course, is the part of the telescope that it was hardest to test on the ground because it needs to work in 0G, and you can only test it in 1G. So you have to rely, like everything else, on computer models. We had a finite element engineering software that NASA uses for their missions, and we broke it. So we had to contract the company to build a bigger one that could have more finite elements. So this was really at the edge of what's feasible. One of the things that was done was to build a 1:3 scale prototype of the sun shield. This was small enough that we could deploy in various orientations. So gravity in various orientation, because you hold it on the side, upright, face down, face up, and so on. So even though we couldn't remove gravity, we could see what happens if you change the direction of gravity. And so if you validate the computer model of the sun shield in that way, but still it remains very complicated, and the shape was, and the deployment details were tuned, almost till the last minute to make sure that everything worked. And there are, of course, a lot of details that I didn't go through, but this is the sun shield layers are made of Kapton, which is a plastic. They have two coatings. The coatings are different for different layers, optimized. The sun shield is designed in such a way that photons, that has a little opening, each layer. So photons emitted toward the interior will tend to bounce outside the telescope because you want it to bounce out rather than be absorbed. The sun shield, you don't want it to become a huge capacitor, so of course you have to make sure that it's grounded. You don't want a tear to you're looking at something that has the same thickness as the wrapping you use in the, in kitchen applications to wrap your leftovers. So you don't want something that will tear up. And so there are lines to strengthen it so that the tear would be contained. It's super complicated. And the third question was, yes, I hope they will find a honest, something that we can honestly call a primordial galaxy or primordial object without being embarrassed. So less than 10⁻² solar, I would say.
Yes. Thank you. I was wondering, has anybody started thinking about building a new telescope, maybe to overcome any problems with finding those galaxies? I mean, just how they started to think about James Webb just before Hubble was
yes and
launched.
No. There are two space observatories, one being developed and one in concept study. I didn't add the slide because I thought I would overrun. One is called Roman. It's a telescope about the size of Hubble, but with a large field of view camera. And the purpose of this, the scientific goal of this telescope is to study dark energy. So somewhat complementary to Euclid in Europe, try to do weak lensing and various applications to constrain dark energy. And it will do, of course, galactic astrophysics because it's like Hubble with a larger field of view, but it will not go deeper than this in spectroscopy. Another one that is being studied is a super Hubble with a much larger aperture designed to study the atmospheres of exoplanets. So not a cosmology mission, atmospheres of exoplanets around stars like the sun. So for reasons that I didn't have the time to go into, JWST is particularly good to study planets orbiting red dwarfs. And this new one would be able to study planets orbiting yellow dwarfs like the sun, which is more challenging. And so it would be another challenging observatory. It's called Habitable World Explorer, and is being studied, and people are looking at 2040 as launch date, while the Roman one would be 2027. I didn't say anything because I didn't have the time, but some of my GTO time is actually spent on trying to address the problem of cosmological tension that maybe would have been more interesting for some folks in the room, but we are not ready yet for that. But essentially, our approach is to use strong gravitational lenses where you have quasars that are imaged 4 times. And each of these 4 images have a slightly different path length. And you can measure the time associated to each path length because the quasars are variable, so you can compute the delta T of each. And by using the timing information and the path length, you can recover the cosmological parameters and reduce the error if you have many. The problem, this was done already with Hubble, the problem is that this requires a careful model of the lens. And so JWST comes in by refining the lens model, reducing the systematics on the lens model, and hopefully should be able to discriminate to address cosmological tension, which for those who don't follow is the fact that measurements of the expansion rate of the universe from cosmic microwave background and from variable stars and supernovae are in a statistically significant, say, 5 sigma disagreement.
Yes.
Maybe I have a comment regarding the finding these very metal poor, maybe regions, let's say, in the universe, and because what one can do is to combine maybe JWST with ground-based observation, for example. And from the ground, we can observe in absorption instead some clouds in the spectra of very distant, very bright objects, for example. And in absorption, we have found already clouds which are very, very dense, which could be tracing, for example, the interstellar medium with metallicity which are also 1,000 solar, for example. But then what one can do is to identify in this way, for example, region very, very matter poor in the universe, and then maybe reobserve them with the JWST, because we don't know what is the origin, let's say, of these clouds. Of course, we don't know if then we will be able with JWST to observe an associated galaxy, or if this is just a cloud that with a very small mass maybe, but this is, for example, another option, I mean, to combine JWST with ground-based facilities to find these very metal poor regions.
Yeah, there is also another option. I thought that's what you were saying. The other option is that some of these super metal poor stars must have been progenitors of the Milky Way. The problem is that they could be very, very, very rare. So how do you find that super metal poor star, if it exists, in the hundreds of billions of stars of the Milky Way? So it could be around us, but it would be it's another one where you need luck. So people are looking at very low metallicity stars, but I don't see a lot of progress on that either.
We have time for a couple of questions more, if there are any. No? Oh, yes. Well, two. Ricardo, two, right?
Thank you. Could you tell us a little more about the structure of the early galaxies, far as Webb's observation?
Well, I mean, despite our great angular resolution, it's still limited. So as far as we can see, these are clumpy objects with little clumps. And this remains valid even for those objects that are being observed through gravitational lenses. Gravitational lens not only gives you extra light, but gives you extra angular resolution in one direction by essentially stretching the target. So as far as we know, these are clumpy things, pretty regular, and it takes, I don't know, maybe a little later.
A very general curiosity. In one of the first slide that you showed with the beginning of the process reminds me of a similar thing that is going on in particle physics. You can imagine what. Now, can you tell us something about the cost of the commissioning of the object and of the R&D? And another curiosity I have is you mentioned these 10,000 people, right? Can you qualify that number in a way that we understand?
Yeah. So the cost, the U.S. taxpayer cost of the development of JWST is roughly $10 billion, to which you can probably add at least a couple of billions of European, Canadian contribution and the cost of 5 years of operation. So you're looking at the $12 billion. There was some money spent, maybe $300 million before we started the phase A in early technology development. So maybe, I don't know, $12.5 billion could be an estimate. The 10,000 is a rough order of magnitude, because it's not that, there was this army at every single time. Some people come in, some people leave, and so on.
The question is, how do you qualify them? They are members of different institutions?
Oh yeah. A lot of those people are not part of the science team, are part of the industry partners. So these are people that work for Northrop Grumman or for NASA and so on. And so they are paid to work on these instead of working on a bomber. And they are happy to work on these because they can talk about it at home. And then that's it. The people that worked on commissioning, I think the paper that was written on commissioning has probably about 600 authors. So that approaches the size of what you could call the integrated science team. And the number of people that got guaranteed time on the telescope, and this could be the last one that NASA builds with this approach, it was probably maybe 11, 12 people. However, the large teams then would distribute time among themselves. So for instance, the NIRSPEC, the European spectrograph, from NASA's point of view, only one person has the telescope time. But then within the science team, that was distributed to a broader group of people. But from NASA point of view, about a dozen people got guaranteed time, which means they wrote a proposal, it was peer review, it was accepted, was found to be reasonable. Then 15 years later, they were reviewed again to make sure that it was still made sense. And then finally, it's being done. I don't know if I've addressed.
Okay, so we have come to an end. So let's thank Massimo again.